Good morning. Today we're going to be talking about probability models. So a probability model consists of an action, its sample space, and a list of events and their probabilities. The events and probabilities in the list have some specific characteristics. So each outcome in the sample space is in exactly one event, and the sum of all the probabilities must be 1. So let's take this circle over here as an example to kind of look at that vocabulary. So the action would be one spin of the spinner. And it doesn't matter how many times I end up doing that, but it's one spin of the spinner. The sample space we have is red, red, blue, red, blue. And the probabilities we have are, we have 3 out of 5 that are red and 2 out of 5 that are blue. When I combine or add those probabilities, their sum is 5 over 5, which is equal to 1. So that's when we say that their probabilities have to equal 1. So meaning we've talked about 100% of the possibilities. Let's keep exploring this vocabulary down here. It says, which list of probabilities does not complete a probability model for this action? So our action says choose one card, and our sample space are these 6 cards here. Our first list says possibility of fewer than 3 shapes. So if I look up here, once again, I have 6 total cards, and I have 2 of them that have fewer than 3 shapes, which would be 2 out of 6. Now that reduces down to 1/3, or 1 out of 3, or 1 for every 3. The possibility of at least, or the probability of at least 3 shapes is 1, 2, 3, 4, which would be 4 out of 6, which reduces down to 2/3. Now 2/6 plus 4/6 equals 6/6, which equals 1. And even in our reduced state here, when we reduce down to simplest form, we still find that to work. So this is indeed a complete probability model for this action. Let's take a look at list 2. We have the probability of a fish, or fish in general. So I've got 1, 2 cards like that. So again, that is 2 out of 6, which is equal to the 1/3. Probability of an apple, 1, 2, 3 of the cards have apples. So 3 out of 6, which is where they got the 1 out of 2 from when they reduced. And the probability of a leaf, well, there's only 1 of those, so 1 out of 6. If I take those and I add them up to find their sum as an unreduced amount, works. And it's easier probably to check that than the ones after, because then I would have to go back up anyway to find common denominators. But since the probabilities have a sum of 1, and because it all fits for choosing one card, the action works with this, then this is a complete probability model. On number 3, it says the probability of an even number of apples. Well, that's 1, 2 out of 6. And the probability of an odd number of apples is 1 out of 6. But when I add 2/6 plus 1/6, I only get 3/6. So since this does not equal 1, then this is not a complete probability model. I did not account for all the different actions that could occur there. So not all of my cards ended up as a possibility. In part 2 here, it says a probability model based on using the theoretical probability of equally likely outcomes is a uniform probability model. So before setting up a probability model, you need to ask yourself, can I use theoretical probability here? Or do I need to collect data and use relative frequencies, which would be that experimental probability? So this first example says, tell whether you can use a uniform probability model for each situation and explain your reasoning. Situation A says a city planner, and this is actually what my husband does. A city planner wants to know the probability that a car waiting at a stop sign will turn left, go straight, or turn right. Well, there's 3 different possibilities there. But if I want to actually look at street planning for a city planner and I want to know this information, I can't just say that they're all 3 equally likely. I need to figure out what might cause something to be more likely than the others. So this does not have equally likely outcomes. And is based on or experimental probability should be used since cars might be more likely to turn in a certain direction. For instance, if going to the left there's a Chipotle, I know at least by my house there's always cars turning into there, and there are cars more likely to turn into there than to say turn right and go into the Domino's. Just saying, it's my personal preference, but I also see that a lot of other people do that. So I can't just say that they all have an equal likely outcome, especially as a city planner. I need to look at what other conditions are around that area that could cause the theoretical probability to be skewed. So in this one, you definitely want to use experimental probability, and that is actually what my husband does. Like, he takes a look at, and they have counters, so that if you've ever been in a car with your parents and you go over and there's a little bump, that is actually a counting device so that city planners can keep track of how many different cars go different directions or cross over that certain point or use that intersection. So they are doing experimental probability at that point to determine what needs to happen there. Do roads need to be widened? Do turn lanes need to be added, or turn signals? So that's very important for them. That's definitely experimental probability. In situation B, 2 friends on a walk are playing a game. At each intersection, they choose at random from 3 slips of paper. They can turn left, go straight, or turn right. What is the probability they will turn left, go straight, or turn right? Because all of these are equally likely, there's nothing else determining which way they go except for those 3 slips of paper, then this situation has a sample space. And this can be done as theoretical probability. They would each have a 1 in 3 chance of being chosen each time they put the slip of paper back in. So they always start with the 3, and so each intersection they go to is going to have an equally likely set of outcomes. So this sample space, so this has a sample space. Of equally likely outcomes. And this can be used with theoretical probability. And now they could go out and do the experiment and then find out which one happened more. So they could do both, but they could absolutely do theoretical probability here. This next part, part 3, says the table shows data collected from 4 cashiers in a grocery store. Write a probability model to find the probability that a customer will use each type of bag. So this is definitely experimental probability. They've actually gone and they've calculated the number of requests, because obviously if you have plastic or paper, they should be about 50%. or I'm sorry, and reusable bags there. So they would each be about 33.3%. But that's not what happened. As you can tell, they don't have even numbers here. So the first thing I'm going to do is I'm going to add all of those up. I need to find out how many different people went through, because that's going to be the bottom. That's going to be my possible outcome. So I want to find out my possible outcomes. So I got 350 total possible outcomes. So in terms of plastic bags, so the probability of plastic is 252 out of 350. Now I know I should reduce this because I can see that they are both even numbers. So I know that I can reduce them at least by 2. And when I divide by 2 here, I get 126 over 175. Now before, I also told you that I can turn these into percents. So that means about 72% of the time people choose plastic, or 72% of the people chose plastic. That's going to be changing because, as you may have heard, Kroger's going to be getting rid of plastic bags. Now the probability of paper bags, which sound better, but environmentally tend to actually be just as bad for the environment. I'm unable to reduce this fraction by 3, but I can reduce it by 7. So I can get 3 over 50. Now I can also write this as the percentage, and this would be 6% of the people chose paper bags. Now the probability of reusable bags, sorry, I added the E in there, I need to keep that out, is 77 over 350, which is 11 over 50. Which is 22%. Now, before we said we need to be able to add these up. So I should be able to add those up and get 350 over 350. I can also take a look at the percentages here, and they should also add up to 100. So we've talked about 100% of the people that were in that experimental probability situation. If you have any questions, please feel free to contact us via email or Google Hangout.